All right, time for another DraftPhysics.com, DebatePhysics.com also, video presentation. And so it's another video, part 2 of Chris the Brain. So kind of a bold statement, but he's also a coward. So it's Chris the Tubby Coward. Because, look, I posted a link to my video as a response video, and, there's plenty of comments. It's going to disappear. No one's going to see it. And he still had to delete it. So, pretty petty move, frankly. And, if people can't take the minor a bit of hostility, you're just not allowed to disagree with these people. And they can't make a counter argument, and so that's why they have to shut it down. But whatever, it's the way of the internet and such. So this will be part 2, and I guess I probably won't bother for the big punchline, because here he does talk about the evidence and does it in the standard, just complete bullshit manner. So, nothing to do with the actual experiments and what they actually demonstrate. So, leave us play the video.
It's easy for us to think of light going in a straight line because most of the time we experience it, it is.
Here we go.
But where this gets troublesome is when we confuse in our experiments a stream of light with the idea of a single photon. And we will cover that here as we go.
All right, so the idea of a single photon, like I said, is just as mushy as understanding a stream of light, because there's no way to make single photons. And it appears that there's all the kinds of evidence that photons can be rendered in different ways, in the sense that you can have more than one source for the elements of a photon.
So to end this section, here's the bottom line.
Bottom line? The bottom line.
When we're talking about the idea of light from the perspective of a single electron, light is not a particle. It exists basically in two main ways.
Okay, so again, he didn't cite any experimental evidence. So this whole thing, he's drawing this conclusion without really citing anything as evidence of why I have to believe it's a silly wave in something.
How you look at it. In a single photon form, it is a ring. An oscillating electron produces a ring of potential photon interaction.
In what? A ring of what? A field of what? A mechanism what? How? Nothing. And obviously it doesn't behave that way because it lands on a surface as one discrete thing. Always. Always, always, always. So if you reduce the amount of photons till you get to just one, the fact is there'll be just one thing hitting a spot, and that's it. Now, there's not really just one photon because, again, we can't make anything that creates one photon. What we can do is put a bunch of filters in front of photons and break them all. So it's sort of like the microwave, right? The microwave has a bunch of holes in the window. What are the holes there for? Well, they're ensuring that the hole is smaller than the polarization of the microwave, and so no microwave as a whole unit can get through, and only pieces can get through. So all you can do is maybe put together some microwaves and a small number of them from different sources, but you can't the original microwaves are all been in some manner or other fractured. So the pieces of the microwave get through, not the microwave.
Interactions. But when we're looking at a single photon interaction from one electron to another, we are looking at a rectangle where all the conditions required for one electron to stimulate another is contained in this rectangle.
So again, I like the idea of just recognizing a photon is thin this way. Again, it's big this way. But let's understand, the rectangle is 500 to 1,000 atoms high. It's not going to be hitting a single electron, and a single electron can't make it. So it's kind of silly to talk about the polarization and not acknowledge the polarization isn't the thickness of an electron. The polarization is gigantic. I mean, 1,000,000 billion times bigger than an electron. So a single electron can't make a photon. It's just not a realistic statement.
And this rectangle is basically stacked around like a ring around the emitting electron. Now, that
doesn't happen, not the truth. You don't have any physical evidence for that.
have that idea of what light really is and what photons, which don't exist, are actually, which are just, again, interactions. Now we're going to take...
Everything is just interactions. So, but obviously I would agree that the idea of what a photon is it's traveling on something. There's a carrier, all right, and the photon is a pattern made out of the carrier. The carrier are discrete bits of quanta, energy quanta, and you've now compressed them into a frequency. 6 of them are in this space here, 6 of them are in this space here, 6 of them are in this space here, that kind of thing. You have changed their density and thereby created a frequency on top of them. It's just no different than sending Morse code.
Take a look at many of the big experiments that we use to observe this wave-particle duality, and you will see this simple physical explanation.
All right, it won't work. No, you're full of crap. Sorry, this jiggly crap is just that crap. You push. It's a push-averse. And the pull is the absence of pushing. So pulling is I'm not pushing. There is no pull. There's just the push.
Fall into place consistently across all of them.
Bullshit.
If you stop
Okay, another commercial. There's an annoying number of them. All right, don't know if I got this right. I probably missed this section, but you probably won't miss it. Anyway, full of shit, nonsense, bullshit. There. Okay, see what else he says.
About the first legendary experiment that made us think of light as a particle, and that is the photoelectric effect.
All right, so obviously the double slit is a lot more famous than the photoelectric effect, so I say kind of bullshit for this one too. But anyway, this certainly is a particle experiment, so there's, in my opinion, no rational way of getting away with that. Not recognizing that it's in discrete bits.
This is the thing Albert Einstein actually won the Nobel Prize for. Surprisingly, not general relativity. It was this. So the photoelectric effect was...
So, I mean, again, I don't know, I'm pretty certain that Einstein would appreciate that the funny tongue thing should just be used once in a while. It shouldn't be the icon for Albert Einstein. I'm sure he says, gee, you could show me a little respect now and then. I was just goofing on the media assholes asking me what it's like to be the smartest man in the world. And, I did the appropriate gesture,
It's a continuation of work by Max Planck, by which we get the Planck length from, around observing black body radiation. These works mark the birth of the ideas behind quantum mechanics in the early 1900s. Einstein's paper on this was published in 1905.
So it wasn't anything to do with quantum mechanics. It was something to do with, discrete, probabilistic, inevitabilistic, functions of energy quanta.
The photoelectric effect is an explanation for two main observations. So first of all, that when shining light at a metal surface, electrons were ejected from that surface when light exceeded a certain minimum frequency.
Right, but electricity was created without the minimum frequency, so you could create the electricity. It still worked better with ultraviolet light, but you could do it with other forms of radiation. So even infrared, we've now have synthetic objects where if you hit them with heat, all right, you will create electricity. So the function is built into light itself, and all you're saying is there's a certain amount of energy you need to actually eject an electron, and the fact is, or a certain circumstance you need to be able to break it. So it's like saying, how do you break a pane of glass? And you could say, well, I can't throw big things, okay, that cover a big surface area. That won't do it. I need to throw little things, and I need to cause a crack or a fracture, and then the whole thing will break. So,
No matter how intense the light was, no matter how much light was shown at it, the only thing that influenced how many electrons were kind of kicked off of that metal surface was the frequency of the light.
Well, obviously it matters how much ultraviolet and how high a frequency it is. So both matter. You have to have the number of photons and a frequency.
And this was a little surprising to us because we figured the more intense the light or the more light there is, the more energy there must be. But it was only the frequency that mattered. The kinetic energy of the ejected electron also depended only on the frequency of light, not the intensity.
So again, that's true. Okay, so obviously you can't give it more speed than the speed that you're introducing the amount of velocity. So this is a simple argument where you're giving velocity to some object, and if you hit it and allow friction to slow it down, and then hit it and then let friction slow it down, and then hit it and let friction slow it down, it'll go less distance than if you just give it all the energy in the very beginning, get to a high velocity, reduce the amount of friction, then it'll go much further. So the idea is it's not about more energy, it's about how you're applying the energy. So the point is the photon has a certain amount of ... and the more compressed you can make that delivery, the more likely you are to get a high enough velocity to escape an atom. That's the simple, I think that simple description will survive the test of time, okay, because it's the simple answer and it's right.
In other words, the higher frequency of light
This is about how to give an object momentum, and doing it slowly doesn't work as good as delivering it quickly. Simple truth. Especially if you're going to deliver it in clumps by throwing something. The faster you can throw the things, the faster you can deliver the energy will do more apparent work. It's not real work. It's just apparent because you're overcoming whatever forces of friction, whatever forces of drag exist, you're overcoming them with the high velocity.
transmitted, the more energy to the receiving electrons, and the intensity of light made no difference. So the two big things that came out of this experiment was, again, this idea that light is both a wave and a particle, but also this idea of quanta of energy.
No, I don't think either one of those had anything to do with it, and it was really just a statement about the idea that there's no half a photon. There's no quarter piece of energy. It's in these clumps.
And this is where we got our original equations for energy of a photon, which we've been using through the script.
And it's just this HF is just about the fact that the frequency is controlling the speed at which you are going to be delivering the energy. And the faster you deliver the energy, the more motion you'll get out of the delivery.
The real reason that we got the idea that light must be a particle from this experiment was because when we observed light knocking off electrons on our surfaces, it only happened at certain points. So it wasn't spread out, consistent. It was happening at points on the display. And that doesn't make sense. If it's a wave, the whole wave should influence the metal surface. Why is it happening at specific points?
All right, so I don't know whether they went into that detail to say that the electrons were actually being launched from specific points because they were getting hit with energy at specific points. But clearly they did describe a well that the electron was stuck in, and the idea is how do you knock it out of the well? And again, my argument is a tipping point is a better argument to understand that it's just resonant frequency. If you want to add energy to a system, you hit it while it's moving in the same direction you want to add the energy. Then it's all additive. If you hit it when it's going the opposite way or after it's slowed down, your energy, you're not going to get your peak amount of velocity. And what you're seeking is a peak velocity.
Must be a particle. But now that you understand that the wave of light emitted from an electron can
all right, so the wave of light from the electron. So the electron can't emit a photon. It can only emit one element of a photon, what will become a photon. So I need energy to go up the entire antenna to make a radio wave. If it doesn't go, then I'm not going to get anything effective out of it. That's why my antenna needs to exist. If the antenna doesn't exist, it doesn't do it very efficiently. So the whole point is that, yes, I need it to transmit through the antenna and hit a whole bunch of atoms and force a whole bunch of electrons to move to make my photons. One atom, one electron moving won't make a photon.
Only affect another electron under certain conditions. Now we know why we observed light in points. And to drive home this point,
so I don't see that at all. So his wave theory pointed out how it should be spread out. It's not. So it doesn't make any sense at all.
I want to show you an experiment done by Action Lab here on YouTube.
Gimmick lab, but fine.
Now he's using an electroscope to show the photoelectric.
Right, and he's using one that really can absorb a lot of electricity. So this is a little bit, he's taking clips out of the video. I didn't watch the original video, but this is like a real mechanical electroscope. So this isn't gold leaf, So you're going to need a lot of charge to charge this electroscope.
Effect, and ironically, he's using this video to show why light is made of particles. But
so you'll see this right in the beginning. Watch this.
We're going to explain it a bit differently. Now, basically,
so he's creating the charge, putting it on the electrons on the balloon, and now he's going to transfer them to the electroscope. And just look at how weak it is. So he obviously had to do this more than once to build up the charge.
The way this works is he has a plate on top that gets charged. He's using static electricity to charge it, and he has an indicator in the circle that is repelled from the plate.
Look how lame that is, right? That is really lame. So he's going to have to add more and more. So now he cuts.
As it gets charged. Now, first,
hey, look how much it is. So he did it more than once. He added a whole bunch of charge. So there's a lot of extra electrons on that plate. It's not just a couple.
First thing I want you to notice is that when he touches the plate with his finger,
obviously he can pull a ton of electrons. Really, you can take a lot of electrons off of a surface, billions of them, without you feeling it. So yeah, that's really easy.
Charge, or the extra electrons, move from the plate to his finger almost instantaneously.
So it wasn't close to instantaneous. It moved pretty slow. It just kind of, okay, I'm going there. Nothing anywhere near instantaneous. So that's just absolute bullshit.
It happens very, very quickly.
Look at it. Come on. That's, very quickly relative to what? A tortoise with 4 broken legs?
But as this video goes on,
all right, so now he's shining this light that has all kinds of colors in it, so only a tiny portion of it could be in, an ultraviolet range. Probably none of it, frankly. It's LEDs, right? So, the LEDs, unless you have built into them the blue ones, you're not going to get anywhere.
And he shows the difference here between how intensity doesn't do much, and he switches to his high-frequency light to now
all right, so now one that's a higher source of ultraviolet. But again, it's not really designed to be an ultraviolet producer in the hardest ranges, the hard ultraviolet. It's a soft ultraviolet light. So it's going to take it some time because it's not, it's on this, it's way over right next to, okay, the green light. It's the blue light. It's just right next to blue. It's not way over here towards X-rays.
Show that the high frequency is ejecting electrons. The thing I want you to notice is how long it takes.
Right, because of the electroscope he's using, it already contains a large charge, so it takes a while to get rid of the large charge. The electrons are piled on top of each other, and you have to get through the layers of them. You could even make it that simple an argument. But if you saw this experiment with a foil electroscope, it collapses quite quickly because it's holding a smaller voltage.
For light to eject those electrons. We know they can move quickly because he did it with his finger. But when he's using the light, it happens very slowly.
And you also know that those lights take a while to really start producing. Fluorescent lights are famously slow chargers.
This is because interactions between light and electrons works like a lottery. We're talking countless photons being sent out so that we get lucky and have a few of those match up perfectly with the electrons so that the energy is communicated and the electrons are ejected.
So it's not really true because, like I said, we just changed the frequency. It happens much, much quicker, blah, 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 blah. So it's yes, of course, it's always random what electron you hit. You're not going to hit every single electron on the surface every single time. But clearly there's a ton of photons going to be hitting a ton of atoms. And it has to hit the atoms in a crystal. All right. And what it's basically doing is, synthesizing electricity, and except that it's more electricity than the material can contain, so it shoots the electrons out instead of just creating an electric current.
So the reason we see these point-like interactions isn't because it's not waves. It's because the conditions for the waves to line up with the electrons just right is so strict that it happens so infrequently compared to the amount of photons that we are shooting off.
I'd say it's a really obscure and almost meaningless point to make, that even if it were true, so what? That doesn't prove wave versus particle. It just proves that electrons are hard to push straight down and then they have to straight up, or whatever your argument is. You know, if you push them at an angle, maybe they don't fly out as easy. So maybe it has to be nice and perpendicular. Maybe there's rules like that. So what? I mean, that doesn't prove wave versus particle at all.
So after the photoelectric effect experiment, caused a ruckus, there soon came another experiment closely following it that really sealed the fate of us thinking of light as both a wave and a particle, and that is Compton scattering.
So this is the irony. I mean, he's basically describing the arguments against, waves, and he's pretty much making it obvious that, yes, they're good arguments.
So this experiment, which took place about 1923, was done by Arthur Compton, so hence Compton scattering. And basically, we take X-rays and shoot them at a graphite surface. Now, what they observed is that for electrons that were loosely bound to the atom, the high-energy X-rays, which we're still calling light, those are light too. Again, they're all light. So the high-frequency X-rays would hit these electrons in the graphite, unbinding the electrons, so knocking them off.
So again, they're hitting atoms, and there's obviously electrons are part of the atom. So obviously that's the part of the atom that is engaged, in terms of the outside of the atom. So you're more likely to be hitting that. But that's all I would argue. And clearly it obviously just points out it's a matter of momentum, and you're just, the fact is if you're going to, move an electron, it's going to move through space, and that movement through space is going to be based on its momentum, and you're just going to get a new photon in the sense the electron will push this way before it goes that way.
And then the light would go in the other direction, and they would kind of go in a symmetrical split up to.
So he's pretty much arguing for angle in, angle out, I guess. Yeah, sort of. I have to look at this. So it's going in this way. It's going to really tight to the surface. I don't see it producing perpendicular, I guess, but that's the argument, is that somehow it's hitting the electrons, and because it's at a tight angle, it's going to push into the surface, push the electron in this way, and the electron's going to repel out this way.
About 180 degrees.
So you're pushing it essentially into a magnetic field, you could argue, or the electric field of the electrons, their repulsive field. So you're basically just pushing on an electron. The other electrons are basically creating a spring effect, and they're going to push the electron back out. And the further you can push the electron in, the faster it's going to leave the surface. So obviously with X-rays, you're going to give it a lot of boom, a lot of pushing quickly, and hit it deep into the atom, and then the atom is going to shoot it back out at a high velocity. And what you're going to end up with is an oscillator where your frequency of your wave coming out, your X-ray, is going to lose frequency based on how much energy it gave the electron. How much of a change there is in the direction of the electron from the energy that went in will be the amount of energy that you have changed the frequency of the X-rays leaving. So the X-rays will lose frequency by interacting, by pushing electrons. And it just makes sense that they would, in the sense that it takes time to push an electron.
Observed is that the smaller the angle of the split, the less the frequency of light was diminished. But as the angle increased, going all the way up to 180 degrees, with the electron going one way and light going completely the other way, we had the biggest change or decrease in frequency of the emitted light. Now, in trying to figure out why
the X-ray scatter, so the scatter of the X-rays is at a lower frequency, and the more the electron is deflected, the lower the frequency. And the less you're deflecting it, the less the frequency change. So it makes perfect sense. Particles don't have a problem with that, blah, blah, blah.
Why this occurred, Compton went back to the equations Einstein had from the photoelectric effect, which assumed light was a particle. And he brought those into his math to show why this was occurring. Now, this is one of many rabbit holes that we're going to have in this video. I actually intend to do a mini follow-up video just on this experiment so we can take a detailed walkthrough of the math and kind of where we went wrong. The bottom line is this all comes down to special relativity, a principle which I covered in my previous video.
I think it all just comes down to the fact is that electrons move slower than the photons hitting them. And that takes time, and that time is going to change the frequency of the bits leaving because you're moving the electron, and every time you move it, okay, you're pushing one way and you're expanding space the other way. So you're just creating a new oscillating. The oscillation will be different going in than coming back out.
Expanding on the idea of the light compass. But basically, if you have an electron that starts oscillating, but then gets shot out of the atom, and so it's going one way, but...
All right, so he's saying it got shot out of the atom and it's still oscillating for some crazy reason. So this is the part where, again, you're giving a discrete thing, piece of energy, to momenta. You're saying that somehow it can be going this way, and at the same time it goes this way, and then it goes this way, and then it goes this way, and then it goes... How does it do any of that? I mean, it's crazy talk. It can only have it's a vector. It can only have a vector of momentum. It can't have a pre-arranged this crap. There's no way it's doing that. And even if it was, how would that create an effect anywhere? And how would that affect the X-ray that's caused the electron to fly off? How is this going to create a photon?
Still oscillating, then you have EM waves being generated, now producing a stream angle on the other side. Those are basically just going to be redshifted. There is going to be a kind of a stretching out relatively of the frequency of light. It's perfectly normal. It makes perfect sense. It's just special relativity. And
so, no, well, whatever. So he's saying that he's going to use some mechanism of special relativity to somehow say that based on the angle of the interaction that somehow I have created this spatial difference in how quickly the source is oscillating, you could argue. And yeah, I'm saying no. Yeah, no, that doesn't make any sense. It's just the time you use to move the electron. Electrons move slower. That's the time delay you're creating.
Light waves. There's no reason for a particle in this experiment. So the biggest problem with the Compton scattering experiment isn't just that it sealed the fate of us thinking of a photon as a particle instead of wave, but that it contains a logical error that has persisted for almost 100 years that has caused us to misinterpret quantum.
So I don't see there's any logical error in recognizing. Yeah, I'll just stick with the obvious. When a photon hits an electron, the electron doesn't move the speed of light. It moves with momentum based on how many bits of energy hit it. So it can move fast if you hit it with a gamma ray, something with a lot of energy delivered quickly. But it's going to move incrementally a speed, not just one speed. An electron can go any speed.
Interactions and fail to understand other things that we observe, some of which we'll get to later. That logical error is assuming that what we observe in a stream of photons is perfectly applicable to a single photon-electron interaction.
All right, so there's no single photon-electron interaction. That's the simple argument. So none of it's applicable. Photons need to hit an atom. They can't hit an electron. So there's no evidence that photons hit electrons. You can't shine light on electrons and create an electron shadow. I mean, there's all kinds of examples. They're just not capable of absorbing an entire photon.
So, as we showed you before, when you have many electrons next to each other or together oscillating,
So this was another bullshit, where they're basically saying, look, we have round things creating round waves, and the round waves are hitting each other, one going this way, one going this way, and that creates a wave going that way. When there's no evidence that photons interact with photons, there's no evidence that that can possibly happen, and there's certainly no experiment demonstrating it.
That is what gives directionality to light, because the sides cancel out, and now you have a stream in one direction.
I mean, lasers are sort of proving the particle argument also, the idea that you're, create a resonator, all right, and you have to have an outlet that lets some portion of the resonant energy out, and it's not wave energy.
When the X-rays hit the graphite, it is a stream of X-rays, it is ejecting a stream of electrons, and for a brief moment of time, as the electrons are ejected from the graphite, they are still oscillating.
All right, so that's the part that you've got to be able to say, oh, bullshit. It's one thing to say electrons are oscillating inside an atom, with the tension. All the other electrons are all pulling on each other and all stuck oscillating somewhere. But once you liberate them, they're not going to keep doing whatever this is. There's no forces that are causing all that tension. So they're in free space. They're not going to be jittering anymore. They're not going to be doing this as they move this way.
Producing a coherent stream of light in a direction. But if we were able to run this experiment, ejecting only one electron at a time, we would find that the photon detection is unpredictable. And that, by the way, my friends, is what we call falsifiability.
Oh, well, that's kind of silly. You're not going to, you're some portion of the energy is obviously being absorbed. So if you use one photon, you have no expectation that there's going to be any reflection because you've already used it up, so to speak. You're not going to have enough energy to create an X-ray. You're really reducing the number of X-rays. Besides reducing the frequency, I would argue the number of X-rays you're going to collect is going to be much lower than the number you put in.
And I'm hoping someone with a little more money and time tries to run that experiment. All right, so the more interesting experiment, and certainly the one that takes up more time here on YouTube and catches more science journalism headlines.
Thank you.
Is the famous double slit experiment.
Did you know?
Commercial right in the middle of it. Poo. All right, continuing.
So for those of you who don't know what the double slit experiment is, again, I'm not sure how you found this video in the first place because you had to have watched it like half a dozen times before this one. But anyways, let's just do a quick review. Feel free to fast forward if you already know this. So in this experiment, we take a coherent light source. The point is it's usually a laser. So we take this laser and we shoot it through a barrier that has two slits in it. Now these slits, in order to work, the size and spacing of these slits have to be related to the wavelength of the light that's actually going through them, or you don't get quite the effect that you want.
Okay, so just bullshit. You don't get the effect you want, which means you don't get the actual patterns that actually happen if you have slits that are actually open. So again, just more horseshit. If you have open slits, we've been over this so many times, but there's a real distinctive pattern, real distinctive double slit pattern. All right, two patterns in one. All right, and that's the truth of it. And it's really not the double slit because that math won't work. Two waves don't create this pattern. So if I have two open slits, I cannot possibly get a right answer, all right, if I use the wave centers. That is, if I assume a wave went through here and a wave went through here and I use that distance, I'm not going to get the right answer because it's bullshit. If I want to know where these little dots are spaced, then I just take this distance. That tells me what the distance will be between these little dots. And if I want the envelope pattern, if I want to predict that mathematically, then I just take the distance of the width of the slit, all right, or the width of the impediment, or an average between the two. And that'll tell me the envelope pattern. That's the truth of it. It's the force surface experiment, the force source experiment. And we know that a single slit makes a huge amount of pattern. I think he's going to say that single slits don't make a pattern. And, you know, it's just bullshit. But I mean, that's the truth. The real pattern doesn't have anything to do with the videos on YouTube. Okay, none of them deal with the actual pattern created by a real open slit. So only when the slits are smaller than a wavelength can you turn the 4-source experiment into the 2-source experiment. And still the pattern doesn't match because there's a double maxima that the math doesn't predict. And it's just a fact that doesn't predict it.
A screen is placed on the other side of that slit. And if we did this right, we should get an interference pattern.
So this won't be the pattern you'll get, okay? It just won't be. This maxima will be twice as big. These won't be that huge. But this is sort of what Young saw, was a bunch of, he didn't use monochromatic light, so the colors bled into each other. There were circles in between the circles, so to speak, of blue ones and then red ones, and so it was all a big mess. So it really doesn't have anything to do with this real subject of the double slit and what you're actually measuring and the actual measurements. The math that works is math that always measures from the surfaces. The surfaces are defining the experiment. It's the distance between the surfaces that is going to decide what kind of pattern you're going to get.
On the screen. And this is the thing that helped us reinforce that light is still a wave. Because
so it's just a cheat, okay? It doesn't do what water does. It's not the same pattern. It has distinct features, like the double maxima. And the fact is, again, the waves have to be on the surfaces. The wave center has to be right on the surface for you to do this as wave mechanics. If you use a wave going through an opening, you won't get the right answer as long as the slit is open. That only works when you make two of the sources so close that there's not a wavelength of difference between those two sources. Then this whole location, the two sources, becomes irrelevant because you can't make a line that's a wavelength longer from those two sources. There's no interference, in other words.
Because even though we're still detecting points of light on that screen, all those points add up to basically these lines where we can see a interference pattern like a wave.
All right, so it's just not a interference pattern. They're very specific patterns created. The double slit and the single slit patterns are distinctly different. So it's all just a big fat lie.
Again, if you have no idea what this experiment is, there's plenty of other YouTube videos that go into it in more depth.
They don't go into them with any depth, and they don't actually look at the real pattern, and they don't explain the real pattern. So bullshit again.
Just a quick review. So the observations from this experiment are as follows. First of all, when just shining the laser through the two slits, we see an interference pattern, which makes us think light is a wave.
Okay, so again, and this interference pattern, again, is made out of what kind of nonsense kind of reasoning? That somehow the only way you can make an on-off pattern is interference? It's the simplest pattern in the universe, and you're saying, no, the only way I can do it is through some kind of interference. When, no, that's bullshit. So the simple explanation is that you're taking a bunch of photons, basically breaking them on the surfaces and throwing the pieces at the surface, and you have a 50-50 chance of being in phase, out of phase, in phase, out of phase. No interference involved. And the radio, again, experiment kind of proves the point. I can have two sources. Those are the slits, so to speak, two sources. I can produce the same radio wave, and then I can have a receiving antenna and just move it back and forth between those two sources, and I'll get on, off, on, off, on, off. Same exact pattern. The waves never even interact. So what's this? It's bullshit. You're just talking about breaking phase. Reconstructing phases.
What's even weirder is that if we shoot one photon through at a time, and then we add up where those photons hit over time.
So again, this is another one of the big lie experiments. Okay, so Veritasium did it. He had to completely break the theory, which is he didn't do it over a large amount of time, making sure there was a tiny amount of energy in the experiment, that is one photon at a time. He had to reduce it, a 5-hour experiment or a 12-hour or 5-day experiment into a 5-minute experiment because he couldn't get it to work. And what did he get as an outcome? I guess it's best if I get that out of the way so you can see it. Some of this stuff you probably should be able to see better. You got a pattern, a nice bar pattern, you could argue, to some extent. I mean, it was very, very weak, okay? But the real part you should understand is it had this huge, this part, okay? So this part where there was this default amount of photons, and it was only this part that was changing, the part on top. So 50% of the photons had no pattern. And that's perfectly consistent with the idea of opening one slit and then you open the second slit. And the argument is that somehow the second slit makes the photon disappear. No, it doesn't. This is as dark as it gets. It doesn't get fully dark. So you're just comparing something brighter, okay, to something less bright. You're not making a comparison between bright and off. So if you really look at the patterns, you can see, even when you have the complex pattern, you'll see that the little missing node is actually there. It's just really faint. So it's still there. There's still photons hitting there, but there's just not as many because it's not getting them from both sources. So it's only two of the sources are producing photons there, so it's weak. And when you have four sources produced, then it's going to be quadratically more intense light because you have more sources to make a photon out of. And simple explanation. But those are the facts. That the single photon experiment was a canard because there was no reason for anybody sensible to think there was more or less than one photon in the experiment, in the sense less than one photon worth of pieces of a photon. There was every reason to believe there was a ton of pieces of a photon in the experiment. All right, that should be enough of that. I have to erase, don't I? Yes, I do. Yeah, okay. All right, continuing.
We still get an interference pattern, making it look like one photon is interfering with itself.
So again, the idea is that they put a bunch of smoky glass in front of the light source to create this idea of one photon. And what is the smoky glass but a bunch of blobs of opaque material that the photon is going to go on those surfaces and scatter and break, and so you're sending a ton of broken pieces of a photon into the experiment.
Which is weird if light's a particle. But even weirder with the double slit experiment is that if we try to observe which slit the photon goes through, the wave interference pattern collapses.
All right, so he's saying it as if it's a real experiment, and later in this very video he's going to point out how you can't observe a photon, you can't observe an electron. So it's absolutely bullshit. You can't, obviously you can't observe photons, but the very idea that you could even observe an electron is ludicrously silly. There's no energy weak enough that you can hit an electron with to observe it. So there's just no possibility. So the very idea that they ever did the experiment is absolute nonsense. And why are we even talking about it? Because we know they can't have done the experiment. So why are we talking about it as if this observing thing is some sort of real thing? It has absolutely nothing to do with reality. There's no such thing as observing it and watching it go somewhere. The only way we can observe a photon is have it crash into something. Then we can observe it. We can observe the collision. We can't observe any other part of its voyage. It's just such a pile of crap. So why is he indulging in this when he's going to debunk it? I mean, why talk about it? Why bring it up as anything other but one of their lies? You should just bring it up as a lie. This is what physicists say that's a complete lie. But everything they say on the double slit is bullshit, is lies about experiments they never did, and they don't even describe the actual patterns the damn frickin' slits create.
It goes away, which is spooky because it makes us think that by observing reality, we change it.
Well, I mean, can't there be one? I mean, I don't think there's one single video produced anywhere, okay, on YouTube. I don't think there's one where they actually show you the two patterns. They just say, okay, look, this is going to be a double slit pattern. All right, and it's going to do this thing here in the middle. This will always be an odd number. Okay, so it'll be 1, 3, 5, 7, 9 little nodes in the center. And this will always be 1/2 of that odd number if you could do it in whole units. So 3 here is 5 there, 6 minus 1. So, and it always fits this mold, right? So if these are 2s, then this is a 5. If these are 4s, then this will be 4 plus 4 is 8. It'll be 9, right? Or, yeah, 1 less. It'll be 7. And that's it. 4 is 7. 5 is going to be 10 minus 1, 9. And it'll just keep doing that. So that's a really interesting fact, okay, is that is a fact. It actually happens. Is there a video that explains that happening? Now, the only one I've seen is Brozo, right? He's the only guy who figured this out, that said so on the internet anyway. It's the only video I ever saw that actually said, yeah, that's the way it comes out. And the single slit is this. This is the single slit. So it's doing the same thing in the sense that it has the double maxima. All right, and you got, your little dots. And you can have 100 of those. Now, you can make it, if you make the slit really, really thin, you can make the pattern look like this. Okay, yeah, you can make it look like that. Okay, so, you can have a variety. I can have a whole bunch of nodes here in the center. I can have very few. So I can make it look different ways by having it a different amount of opening or a different amount of impediment. But that's the reality. So what are we talking about? Some sort of standard interference, a pattern? There's no standard pattern. The fringes can take all kinds of form and have real rules that govern them. And again, the real rule is, in the double slit, is the outside dimension, the 2 furthest surfaces, will define exactly where the little nodes will be, the size of them, and the smallest dimension will define your envelope. And that's the fact. It's a surface phenomenon, proven fact, essentially. I mean, it's beyond reasonable doubt, frankly. You can't reasonably say, oh, yeah, no, it's not the surfaces, because the surfaces are completely controlling the experiment. They're obviously the point sources. The stuff that's making the pattern is coming from the surfaces. It's not coming from the middle of the slit. Yeah, that's not what I wanted to do. I wanted to do this.
Okay, so let's explain all of this real quick now. So first of all, the fact that light interferes with itself, that's fine, because light is a wave. We've established that. Light is a wave.
No, it's not even, it's just established it with just distortion and perversions and outright deceptions. Inaccurate statements regarding what the experiment actually shows.
Even one photon, going through at a time is still an entire wave passing through both slits.
So he says it's an entire wave passing through both slits. Like I said, if you open those slits, that won't work. So if those slits are something more than a wavelength opened, all right, the fact is you're going to get the more complex pattern, and you have no hope of explaining that with your wave theory. No hope at all. The math doesn't work, and your drawing won't work.
The reason we only detected at one point is the reasons that we went through before.
Yeah, I don't know what reason there was. You didn't give a reason why it goes to one point. You didn't explain why it's making all these cards going all these places. Why does the only one card actually land somewhere?
But the thing that boggles everyone's brain is, why is it when we try to observe which slit the photon's going through?
So this has nothing to do with anything called observing. It's just such a perversion of reality. The universe is constantly observing everything. Okay, gravity is everywhere, and it in effect is taking a picture of everything all the time. And if we could see that film, you'd know that nothing is in 2 places at once, and nothing is superimposed, and none of that crap is true, because everything is de-entangled. You can't go anywhere in the universe and pretend, I'm entangled, I'm superimposed. No, because you're getting seen by gravity. You're done being in your magic state.
Does the interference pattern disappear? That's the one that makes everyone go, ooh, okay? So let's just address that one flat out. When scientists say we are observing which slit a photon goes through, they are lying.
Yes, exactly. So why didn't you just say that right from the beginning? They're just lying. It's just a fake experiment. So science is really bad. I mean, it's really kind of evil that they made up this lie that this has something to do with observing a photon. And it has nothing to do with observing a photon. They never did that experiment. They didn't detect crap.
We observe jack shit. As we know, all the way back from the photoelectric effect, we don't observe photons directly. We only observe light through its interaction with other electrons.
No, through its interaction with atoms. You have to actually hit atoms to detect light, and you have to do it to emit light. You can't do it with an electron. A single electron can't make a photon. Doesn't matter what it does. It can't make a whole photon. It can't make something that's 500 atoms polarization fly through space. It can't do that. Not possible.
And we have an electron emitting light, we have electron re-emitting light, we have our eyes, which detect light with electrons. We never actually see the things anyway. What we're just getting is the electrons. So
no, we're getting the electricity. So again, let's understand where we really are. It's always doing the photoelectric effect. We detect the electricity created by the photons interacting with the surface and being their energy being absorbed. If the photons all reflect, then we're not going to have any electricity to play with.
that's where our points are coming from. So we're not watching a photon pass through a slit. We can't. It's impossible. The word observe makes it sound like we're watching as the photon passes through a slit, but we can't. We can't. We see nothing.
We can't test an electron, and we can't test a photon. We can only see what they do. We can't put them through an obstacle course where we can watch them being manipulated by the obstacle.
What we can do is wait until that wave hits another electron. Oh, Chris, but what if we built a detector? Well, guess what a detector is? An electron.
All right, so again, it's an atom. It's not an electron. So you have to have more than one atom as a fact. You're just never going to detect a photon with one atom and one electron. Just can't happen.
It's something that the light can stimulate. And here's the problem. If you have something that is stimulated by an EM wave, what happens is that you create another EM wave. Now, this is the experiment when I originally started.
If you push an electron this way, okay, what happens going that way? Oh, that's right, you just pushed on a whole bunch of force that way. So yes, it's pretty hard to not cause an effect in even if you're going to be reflected. Even if there's going to be a reflection, there still has to be some consequence that makes the reflection possible.
Doing this chapter that I wanted to set up and show. Thankfully, we actually found someone else already did this experiment.
I mean, Bill Gates actually has a good analogy of a boomerang. You know, you could throw a boomerang. All the momentum's this way. You go that way when you threw the boomerang. But the boomerang can come all the way back around and hit you and give you momentum back this way, you know. So the fact is energy can be turned in its direction. It doesn't, there's no rule saying you can't do a U-turn of the direction of energy. There's no law against it. Direction is, you don't need to use any energy to change direction, which is the interesting fact.
Applied Physics Letters published a paper where the authors created an experiment to try and shed light on the double slit experiment.
So now he's going from two basic foundational experiments to some obscure pile of mush, okay, in some modern mush journal.
Now, just as a side note, for this experiment they used electrons, not photons, but I want to note that difference. But the result still proves the point, so bear with me.
So there's no result here, right? We're going to talk about throwing electrons through slits and saying we don't expect the charged particle to be affected by the surfaces, when, of course, I would expect the charged particle to be affected by the surfaces. Duh.
They created a version of the experiment that used a low atomic number material, so that means really, really thin, to detect if a particle passed through one side with the hope of leaving the electron as it passed through unaffected.
So it's just absolute crap, right? I mean, this very idea that you're going to send electrons through a material where they're going to actually cause a visible effect of some kind. Again, just nonsense.
However, even with this super thin material, they found that while the particles passing through the open slit, so the one where we're not detecting it, produce what we call elastic scattering, basically meaning that it behaved like a wave passing through an opening in a barrier, while the detecting slit produced inelastic scattering, which basically means a new wave starting from scratch. And the best way I can describe the difference between the two is just show you this picture. The bottom line is, one of these is the wave as it passes through the barrier, and the other one is a brand new wave. Now,
yeah, and I would argue that this just has to do with the interaction with the material. So, the end. You're interacting with more than one material in one case, and you're interacting with two materials in the other case. Duh.
they don't make the following conclusion in this paper, but you can see that with everything we have explained about EM so far, it is impossible to detect them without changing them or making new ones. In other words, the problem with using the word observe when talking about photons is that you can't observe them without messing with them.
Well, you just said electrons, this experiment. So again, you ought to stick to it. But it's just true. You can't observe an electron. So you could give an electron insane amounts of energy and say, okay, I'll give it so much energy that it can't be deflected off its course, and yet it can still hit another electron and give it some portion of its energy. And even that doesn't work, because well, the electron it's going to hit is going to have the same mass as the object you're using to hit it with, so you're going to lose at least half the energy.
In fact, you can't observe anything in the quantum world at all without interfering with it. And most of the time, we are observing quantum objects.
I mean, you'll lose even more than half the energy if the other electron is actually moving towards you and the two fields are going to reflect.
It is done by shooting them with a laser. That would be like observing the position of runners in a marathon by pelting them with rubber bullets and measuring the angle they bounce off. Gee, I wonder why measuring them makes them change position and velocity. Must be that observation changes reality.
Yeah, well, it's more like, hitting a regular car with a Volkswagen. So, I mean, I think it's more dramatic.
Of course you change reality when you shoot shit at it. That's how reality works, you pretentious morons. The point here, light produces an interference pattern.
The point should be, you should be pointing out how physics lies about this whole observing nonsense, and that they never observed anything, and they do some bizarre experiment and say that was an observation, a benign observation, when there's no such thing as a benign observation. And again, even the whole idea of saying, let's shoot electrons through slits, and have the silly notion that somehow electrons, charged objects, are not going to see the charges on the slits. It's ridiculous.
Because it's an electromagnetic wave. When you push a wave through two slits, you get two wave patterns. Those patterns...
Right, so that doesn't happen. There's no two waves. That's not mathematically going to get you the right answer. So it just doesn't work if the slits are open. At all. Doesn't work at all.
Can interfere with each other and produce an interference pattern because they're waves. If you instead block one of the slits and instead create a new EM wave, which is what's really happening when we try to detect them.
So this is the bullshit here, right? I mean, you're going to get a single slit pattern. And again, it has a double maxima. The water waves don't work. It's not analogous to.
Then the chance of them interfering is very small.
So look how he drew the single slit pattern as a blob. It's not a blob. If the slit is open, it's not going to be that at all. It's going to be a whole fringe pattern. You could have hundreds of bars of on and off. Well, 100. I did an experiment and had 70. I think was the most I was able to make was 70. 70 distinct bars.
And they certainly won't produce a consistent pattern because now they're two completely different wave patterns.
So that's just nonsense. Single slits are always single slits, and if they're open, you're going to get lots of pattern.
But let's not stop here. The double slit experiment has spawned a variety of spin-offs that have provided what are up until now similarly mind-blowing and confuzzling results. So as I mentioned before, we also have the single photon experiment, where it's just one photon at a time going through the double slits and still produces an interference pattern when we...
Okay, so again, you're saying so without proving so, blah, 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 no sale.
add up all the detections over time. And again, of course it does, it's a wave. But here's the other problem I wanted to point out with this. And that's the phrase, a single photon. And
so at least you're right about that. But I don't know why you're talking as if, so that's the problem. You just defended the idea. You're citing a video that claims the idea, and then you're saying, well, the idea is wrong.
Here's where I want to elaborate on this a bit. There is no universal definition for what a single photon is. A single photon is kind of determined by the experiment. For example, during the photoelectric effect, a single photon was described as however much energy it took to eject an electron.
And again, it's not about the energy, it's about how quickly you deliver the energy.
In other experiments, it's based on just what's the lowest amount of energy we can detect a photon. See, here's the thing we're not quite sure about. When I say it takes a full sine wave of...
Well, you're not quite sure of, and their drawings are never quite sure of, and I've been talking about it for 10 years, the fact that they don't give you any description of how many of these little lumpy things make a photon. I mean, it's a pretty glaring omission. One little lumpy thing, or 5 little lumpy things, or 100 little... How many of those do I need?
Motion to produce a photon. We don't know if it's just 1 or 2.
I'd say it has to be more than 1 to have a frequency, but regardless. Continue.
Or 3. Depending
3, I think, is a good number. So personally, that's my favorite.
on the experiment, this thing could be 3 meters long.
Well, we know how... the fact is that the frequency itself could be 10 miles long. The one little thingy. Does that seem realistic? No, that doesn't seem realistic at all. So again, it just makes particles make so much more sense if you just think of me stretching your card to be 10 miles long. The frequency itself, one card 10 miles long to get one oscillation out of the system. When the simple explanation would be no, there's a little bit, and they're 10 miles across at the speed of light. At the speed of light, it takes the frequency. It takes that much time, the period, for one to get to the same place the other one's at the speed of light. So yeah, that makes perfectly good sense. 2 baseballs 10 miles apart makes sense. 1 baseball 10 miles long doesn't make any sense.
We don't know. The smallest a photon can be is 1 sine wave. And I'm skeptical, although it certainly might be possible, that we've ever had an experiment that confirms 1 sine wave of detection. So just a little clarification for you guys too when you're playing at home. Now, on that note, that brings us to the next crazy double slit experiment. You guys may have seen somewhat recently the headlines about this idea of a time slit photon experiment. So this is the idea that instead of sending a photon through slits, we just create these basically attosecond, very, very tiny bursts of light. And we shoot them in a straight line. And to our amazement, we still get an interference pattern. So I have references to these experiments in the description. You can go and look for them, at them for yourself. Now, the fact that shooting these small amounts of light, one after another in a straight line, producing an interference pattern, led to the headlines.
Well, the whole idea that that pulsing the light has anything to do with how many photons are actually in the first pulse, just, doesn't change anything. Meaningless.
Photons interfere with themselves backwards through time. Ugh.
So yeah, there'll really be no evidence of that they sent a single photon with a single photon behind it, and those 2 photons interfered with each other. That's bullshit. No chance.
No, they just interfere through space because they're waves. This is very simple to deduce.
Yeah, it's just garbage. But anyway, you could theoretically do an experiment, though, where you had mirrors, at different distances. And so your photons are going to hit them at different times, okay, but they're going to travel different amounts of distance. So one of them's closer to the target than the other one. So yeah, one of them travels, they end up traveling the same distance after they've interacted with the mirror, something like that. Or you could actually have them travel different amounts of distance, and they'll be at different times the photon came out of the gun. And those two photons will actually create contributions, because that's technically what's happening in the double slit. They're traveling different path lengths, so they're already photons from different distances in time. I mean, you have to understand they have to be at different points in time, because one of them has traveled further, so it had to leave the slit sooner because it's traveling further. Do I have to draw that? Well, maybe I'll draw it real quick, because it's sort of an important point, I think. So, even the traditional experiment where, you have your sources. All right, let's just say there's two sources for the sake of argument. You'd have to still concede this at the speed of light, right? This photon had to leave much earlier. So let's say it's 14 wavelengths difference or whatever. Okay, but it's a full wavelength, 14 full wavelengths of difference. That's going to be an on, okay? But what's it going to be made out of? It's going to be made out of a photon that got here later than the photon that got here. So obviously it's already time invariant. You're already using a photon that got to the slit at a different time than the other one. One of them was ahead, it got here, it's here, and the other one was here in time. I mean, yeah. So, I mean, the regular double slit is already arguing essentially that the photons are obviously coming from different points in time. Because traveling more distance takes more time. Obviously, it had to get there sooner. This one had to get there sooner to be able to travel the longer distance. Whatever. Blah, 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 blah. I gotta erase. Alright, continuing.
If I take water and I just drop little drops of water in a row, you see that as the waves expand, they interfere.
Right, and if I drop one piece of water, I'll get a nice round ring, no interference, no anything. So in the single slit with light, I get a ton of pattern, 70, 100 bars. Single slit in water, nothing.
With each other. It's completely understandable why this would happen. They don't need to be traveling backwards through time. Now, some of you, if you're really paying attention, might notice, though, there is one small problem with this analogy of water droplets I'm using for the light, but I'm going to wait and see how many of you catch it and cover it in the follow-up video. The point here is that all these interference experiments and their spin-offs are all easily rationalized and explained once you understand that what we call the photon, again, is just a small area of interaction.
So it's not a wave, so it's clumps. And all you're doing is you have a bunch of little clumps of energy in the universe, and all you're doing is compressing the clumps and expanding the clumps in space. And that signal is a photon.
With geometric requirements of an expanding spherical EM wave. But to really pull the quantum nuttiness out of photons, we got to dig out the whole root. So let's talk about polarization.
Hi, my name's Dr. Frank Schallenberg.
Poop. Really is, these low wattage channels that have ads, their ads are just abysmal. So it's like YouTube saves all the really horrible, tasteless, nasty, lie ads to put on the low volume videos, because obviously the high volume videos wouldn't tolerate it. But anyway, it's just disgusting. Anyway, making money off shysters trying to steal people's money. It's disgusting. I will never take such a paycheck. Yeah, I really won't.
So we are going to discuss a few observations around photons and polarizations, but first let me explain what polarization is and how it works. Going back...
So you really won't do that. So the real understanding is to understand that it's just chemistry. So it's just, it's just layers. So maybe I'll do that first. So when you find out what this stuff really is, all right, it's so much different than what it's implied to be. So they imply it's a bunch of, you could probably do it with a grating, but I mean, the fact is that polarizing film for photons is really made by just having a layer of material, and then you put a second layer in little tiny rows. So rows going this way, across the material. So if you were looking at the flat material, it has a double row where the lines are, and it's only a single thickness, okay, where the lines aren't. So there's a single thickness and then there's a double thickness. So all it's doing is changing the phase. So you get one phase shift from the one material and then another 90-degree phase shift from the second layer. So that's all you're doing, is creating the half phase change. The two 90s equal 180, the half phase change, knocking the photons, the pieces, out of phase. And the other thing to understand is the polarizer is in this direction when it lets light polarized in this direction through. Okay, so there is no, I originally thought, yeah, it's throwing frisbees through a jail cell. Really easy to do. But that's not what it is. You're throwing the frisbees through the bars. Okay, that's how the light going this way with its polarization in this orientation is going through bars this way. So that also needs to be understood. The radar experiment proves that, which way the bars are actually going. So the microwave antenna is this way. The bars are this way when the light goes through. The light is polarized this way that gets through. Okay. That's probably enough of that little lesson. So he's going to have the wrong drawing here. And he's also going to argue his cards are going through the bars, when no, you have to get the cards to go through the bars the wrong way. That's the interesting part. And it really is, although it's affecting polarization, they really are, polarization has something to do with it. The real thing it's changing is phase. And that's what's breaking the polarization, is the fact that you're changing the phase of part of the photon. And you can rescue it because it still goes through. It's all transparent. So all the light's going through. I mean, they always look dark because of the fact that you're changing the photons, the polarization, so you can't see through it as if it was transparent because it's changing the photons. But the fact is the same amount of pieces is coming through. It's just some of them isn't coherent photons anymore. And the fact is, by putting the half filters in, you can get some of those photons recovered. You can put the double layer where it needs to be to take a photon that went through a double layer and put it back a full 360. So you moved it 180, it's out of phase, and now you can put it back to 360 again.
To our playing card right here, the direction of the y-axis is the direction of polarization. So if this were coming at you, this is the polarization, up and down, side to side. So this direction of oscillation that electron is moving is technically called the dipole moment. It just means it wiggles back and forth on that axis, but scientists love to come up with esoteric terminology for things. There are three ways light can be polarized. So it can be polarized vertically, it can be polarized horizontally.
So, and there's no such thing as circularly polarized light. There's no photon that's spinning through space. That's just nonsense.
Horizontally, or it can be spinning. So circular polarized light.
Chance.
Or it can be unpolarized. But won't get into that right now. That just basically means it's a ton of photon. No, light is always polarized individually. When you just get a ton of them together, they all kind of average out, and we call that unpolarized. Sorry to give you the whole background of polarization. Just bear with me. This will be important.
It wasn't much of a background.
One of the little experiments that get a lot of attention on YouTube here is the 3 stacked polarizers. With the context of our new understanding of light, I'm going to revisit this for 2 reasons. One, it further drives home the nature of light as a wave, and a photon is just a geometrically conditioned interaction. And number two, the true nature of
It certainly is geometric, but I don't know how you do your geometry with a wave.
polarization has a lot of ramifications for quantum mechanics. So let's talk about the three polarizers. What happens is we shine light.
Right. And so which way is that light polarized? So he's just doing this blob thing into the polarizer, so that ain't going to help any.
Through one polarizer. And it only allows...
So he's saying that the polarization is counter to the grid. So that's correct. The grid is this way, the polarization is this way. So now he's got to explain how his card went through the grid without turning this way to get through the grid. How did the cards going this way get through that grid?
Light that is oscillating at a certain direction, so that's our polarization, to pass through. So if I have sunglasses, they may only let horizontal polarized light through, or they may only let vertical polarized light through. That's how we get less light.
I don't think they ever have them turn sideways, because their point is to get rid of glare, and glare is always polarized this way.
Light through sunglasses. But if we take that now and we add a second polarizer oriented 90 degrees to the first one, then that is going to block out all the light, because one of them blocked out everything horizontal, the other one blocked out everything vertical. But if we add a third polarizer between them at 45 degrees, the really weird thing is that we actually end up getting more light through.
Right, we just recover. So all you did was break the phase of the light. So these polarizers aren't very dark, you can see that, so you're not losing too much, 10%, 5% of the light. And the fact is that all you're really saying is if I put the quarter polarizer in, I can do it in stages. I could actually put 10 of them in, and I can get almost like 80% of the light back. So, it's just about the fact that you're just trying to reorient the phase and fix what you broke.
Than with the two. And that doesn't make sense when you think of light as a particle, because if you have two filters that filter out 100%, adding a third filter should filter out more. So what's going on?
So you're denying the fact that the particles are not photons themselves. They are a bunch of particles that have to be in an arrangement. They have to have a polarization. So they have to be in phase frequency-wise, and they have to be the right polarization. And all you're saying is that by having the double filter, the bits are being knocked out of their frequency. They're out of frequency by being knocked out of phase. And you can put them back at the right frequency by just putting them through another 2-layer.
Going on. But again, this is only confusing if you think light is a particle. If you think light are waves, it's very easy to explain the whole thing.
No, I'm sorry. There's just no way that there's anything wrong with explaining it as particles, because it's just about changing the phase of parts of the photon. And I think it's just an absolute fact. The photons aren't destroyed, they're broken. The pieces are still coming out of the other end. The polarizers aren't getting hot. They haven't destroyed any photons. They haven't absorbed the energy. The energy is still coming out, and you can't see it as photons. And that's the absolute truth.
So first of all, what you need to understand is that these kind of polarizers that we're talking about here, they work by having a material where the atoms are so close together on one axis and farther away on another that it basically constrains the electrons and forces the...
So says you that's not how they're made. So I'm just saying they're just made as layers. 2 layers in striping. That's it.
...them to move along only one axis. The direction the electrons are free to move, again, the dipole moment, is the direction in which the polarizers will polarize light. If we go back to our photon card analogy, the direction of oscillation of the sine wave, again, now has to match the axis of the electron in our polarizer where it's free to move in order to perpetuate the wave. That's the key to understanding this whole thing. Polarizers...
So it really isn't. So the transparent polarizers are using a phase shift. If you used metal bars, really tiny thin wire, to make a polarizer, then you can sort of logically understand what you're doing is you're basically creating a bunch of slit experiments. So you're going to start creating fringe photons. What photons wobbling up and down. But as long as you're in the same plane, you're okay. So if the photon was going through this way and the bars are going this way, well, then you're going to wobble them this way and that way. That's going to be a lot harder to reconstruct than if you wobble them this way. So changing their position this way is fixable. If you change their position this way, it's not going to be fixable.
Aren't actually filtering light at all. They are producing new light waves based on how they are stimulated. None of the original waves actually pass through the polarizer. Their energy is transferred from the waves that hit the polarizer to the electrons in the polarizer. And this is all according to an equation that we've had around for a very long time now called Malice's law. And we'll explain.
So there's really no, like I said, it seems pretty unrealistic to think that something that's essentially transparent, okay, is somehow recreating the photon. But whatever, fine. I mean, in some sense, the energy of like going through glass, clearly it's not the same photons because they're not moving as fast through the glass, okay? I mean, they're being slowed down by pushing electrons. So there's every probability that you are just moving an electron in the end. And so you're pushing an electron on one side of the surface and you're pushing an electron on the other side of the surface. And it's just duplicating the effect.
Explain the math of that in a minute, but first let me just drive home the mechanics of how this works. The light which matches the polarizer will stimulate a new wave, pretty much the exact same intensity as the one that hit it. But the light perpendicular to the polarizer is just turned into heat. And the light that is...
Okay, so there's no evidence of heat. So he said it was just turned into heat. There's no evidence. Zero. I've never seen an experiment where they see how the polarizers are getting hot. Never happened. I don't think it happens. I think it's bullshit.
In the middle kind of does both. Half of it is turned into more light and half of it is turned into heat. And the way this works, and we're going to go back to our cards again, is think about if I take this card and I throw it through a slit. If that slit is aligned to the same axis as the edge of the card will go right through.
So now he's got the broken analogy. So his other animation was correct. The bars are going this way. You're trying to put a card through this way. And now he's saying, I'm going through the jail bar. So you can't have it both ways. Only one of those is correct. And the real correct one is the bars are against the polarization. That's the light that gets through.
Without any energy loss. If I throw the card at the slit and the axes are misaligned, the card may still go through, but the energy is lost to the friction and the collision of the sides of the card and the surface. Lastly, if I throw the card at the slit where the axis is completely perpendicular, it won't go through at all. It'll just hit and fall off. The purpose of this analogy is to...
So it's a bad analogy because I don't think anything hits. There's obviously no reflections that are obvious. It's not a whole lot of reflected light. So the idea that the plastic absorbs light, I think, again, is bullshit.
To show you why the effect of light on a polarizer, and many other circumstances, in fact, follows that of a projected plane, which we talked about before.
I think the obvious point is that photons are just a pattern, and the energy is still going through. The pattern is lost.
However, instead of the plane being calculated by how flat it is compared to your view, in this case, it's calculated by how aligned the wave is to the dipole moment of the electron. So in other words, when we're looking...
More dipole moment nonsense, like somehow electrons have something other than just a basic charge, and that's all they have. They don't have any dipole moment.
From the electron's point of view, this would be 100% of the energy, and this is where we start getting lost. So it works like this, and now we'll get into the math of Malice's law here. So for the first polarizer, let's say the initial light source has an intensity of, we're going to just call it I naught, okay, or I0, and it is unpolarized light. After the first polarizer, in this case oriented vertically, only the vertical components of the electric field get through, reducing the intensity to I1 equals I naught divided by 2. Again, assuming half the light vibrates vertically and half horizontally, which is most of the case with unpolarized light. In a stream of unpolarized light, which again is countless EM waves, the average alignment percentage of horizontal and vertical will almost always be half and half because we get it from the sun and that thing's shooting off things like crazy. So for the second polarizer, which is now horizontal, according to Malice's law, in this case theta is 90 degrees, the intensity becomes 0. No light gets through because the cosine of 90 degrees is 0. Now, take a second and notice that our equation here for Malice's law for determining the intensity of light through these polarizers is the same equation that we used earlier to calculate the area of a projected plane. let's add in now our third polarizer. We have the first one, the second one's 45 degrees from the first one, the next one's 45 degrees. And what's basically happening here is that instead of blocking the light, the intensity of the light is simply being taken down at each step based on this equation. So half the intensity from the first polarizer is halved again at the second one and is halved again at the last one. But as you can see, for each polarizer, we are just stacking our projected plane equation from the beginning. The bottom line here is that there is no probability about this. There's no kind of a quantum randomness, except for the fact that from the first beam of light, we don't know what percentage is what polarized. It's simply taking two vectors and calculating the remainder vector of motion visualized here. The reason 3 polarizers at 45 degrees allows...
No, this is kind of bullshit. And the net product is that you go from 0 to 22%, okay, which is a pretty high recovery rate.
More light through than 2 at 90 degrees is because the entire plane of the EM wave is getting reduced as it passes through each polarizer. The angle, the electron's dipole moment, is misaligned to the angle of oscillation of the EM wave.
So there's no other element to something. You have to say the frequency is diminished because you can't do anything else than that. So I don't see how you're going to explain how you have a infrared photon and it's somehow you lost some energy somewhere. It can't give away any energy and still be an infrared photon.
Reduces the plane experienced by the electron. The point here is that polarizers work the way they do because 1, light is a wave, not a particle. 2, only the part of the wave where the oscillation mostly matches the dipole moment of the electron is being detected as light interaction. And 3, because the motion of that wave over time produces a plane.
So too bad you didn't explain what a dipole moment of an electron is.
And we can calculate its effect on an electron via a projected plane. All right, now we're getting one of my favorite applications of this. We are going to talk about nonlinear crystals.
That's how the...
Ew. All right, so I don't know if I really want to play any further. Yeah, I don't know. Nonlinear crystals is just saying, look, you put an ultraviolet in, you get 2 infrareds out. Not very complicated. They use it all over the place, and yes, it's not very good in the sense that it only happens 10% of the light, so you're going to waste an awful lot of energy trying to create your photons that way. I think LIGO does do this conversion, which is kind of funny. They go from blue light to red light for some dopey reason that I can't understand. Why would you use the lower frequency light? It's, can't get as much detail. I mean, it really is. They're shooting infrared light. They create the light as green light, I think, and then they convert it into red light. Why would you do that? Just crazy from my perspective. Anyway, can't make much sense. All right. Morning.